What is a matrix exponential? Now we go there. So, are we together on this one? Very much, not at all, kind of. Why kind of? There's some people that say kind of. This one is scalar.
Because I saw the problem and linear systems, and I used it because I don't know how to find it.
So, okay, no worries.
Yes, yes,
This one
yes.
is scalar. And just in case, also if you are rewatching the videos, this one holds because if I take this and I put it here, and I take this and I put it here in the sense that I derive this and I put it here, what do I get? I get something for which the equality holds, okay? Because I'm gonna get A EAT x0 is equal to EA EAT x0. Do you see? If I take this and I put it here and here, I get the equality. Together, this is like solving differential equations by inspection. This one generalizes to this one. As soon as look at the properties of exponentials. To kind of have this one that goes inside here, we need, first of all, this one. True? We have been using that one. Are we together that we have been using that one just now? 1, 2, 3. And in a certain sense, we also have, since it's time invariant, we implicitly are using this one. This is very important whenever we do actually the convolution. But there's also this one. Whenever we want to work with matrices, we would like the same properties to hold. You see? Because if we have those properties holding also for matrices, then we have the hope for being able to generalize this one to the matricial sense. From a logical perspective, people, are you following me? Are you following the discussion, the intuitions behind it? Excellent. What do we need to do? We need to define this object in an opportune way so that the object that we define has the properties that are the properties that we are looking for. So it's an active definition. We want this, and for example, this one, this is a wrong way of doing it. If you try, so this is a common misconception. Okay, this I saw this happening very often. You take a matrix, you take the exponential, and you take exponentials of all objects. This is not the right way of doing it, because if you do the derivation of this stuff here, you do not get the same thingy. You can verify. Actually, this one satisfies the first property, but the second property, if you look at it, it's not satisfied. Okay. The correct way is with Taylor expansions, in the sense that EAT defined this way will give rise to a certain polynomial that I think we already saw whenever we were discussing about delays. True? Do we remember whenever we talk about delays, this stuff here happens? And we can generalize. Now, there's a couple of considerations that are important to say here. Let's pretend that I've got an A here that is 7. Here I've got 7, 49, 7 to the power of 3, etc. On the numerators, we've got something that goes up. True? Plus, if I take t 10 billion years from now, this is very big, this is extremely big, true? This numerator here looks like it has the potential of exploding very fast. Are we together on this? The same happens for this one. The denominator, factorials, do they explode? Do they explode fast or slow? Very fast. Do they explode faster than this or slower than, sorry, faster than this or slower than this? Much faster. Much faster. Not faster, much faster. This stuff here goes to infinity in a way that independently of what you put inside here, at a certain point, this one will be enough big for which the ratio here is below numerical precision that you might have on finite computers. Okay? Might be that you need this power here to be, I don't know, 10,000, 20,000, but I guarantee you that at a certain point, you essentially have a tail of terms that numerically is zero, analytically it's not zero, but it converges. It goes to zero in a way that is sufficiently fast for which this value here is finite. True? Might be very big. Think that A equals to 10 billion, T equals to 30 trillion. This is very big, means that the tail is very long, but this stuff here converges. How are we together, people? The same. Okay? The same. Take this one, do the derivative. What do we get? If we take this one and we do the derivative, this goes away. Here I've got A. Here I've got this one, eats out this one, true? And I've got an A squared. Do you see it? I think you should be able to see it from a looking at it point of view. And this one is much more difficult to verify, but I guarantee you that it holds. It's cross products of all the terms. It's kind of a mess. But as soon as you define things with Taylor expansions, it's fine. And this is very interesting also because we can generalize even further. As soon as we have e to the power of star, or better, as soon as we can say star for a scalar and star power of something, if we are able to do this with any object here, then we can do e to the power of star through the Taylor series. So it generalizes beyond matrices, but we don't see. You might, depends on the courses that you will see. Okay, formulas that we don't care. We should be together. Are there questions, people? No. Am I recording? Perfect. Now, if we go back to the original problem, if we want to solve first order ODEs, it means solving this stuff here by defining EAT as we were seeing before. We do not see the theorems, but essentially we have a structure for the forced response plus free evolution plus forced response that is essentially the same that we were seeing in scalar systems, only that this one is a matrix, this one is a matrix, this one is another matrix. This is not a vector, it's not a convolution, a scalar convolution, but it's essentially a matrix of convolutions, component by component. But from a qualitative perspective, the operation is the same as before. Okay? So by defining this, we inherit all the theorems and the concepts that we saw in the first part of the course to the scalar case. What is missing? It's missing to compute this one because we do not know up to now. It's kind of, we are using it as a symbol for now. So we need to compute the values inside, but essentially we are at a point for which we say, okay, the math is the same as before. And this one is the impulse response, true? You see that this one is the impulse response? This one is h of t, h of tau, true? it's not anymore a function, it's a matrix of functions. Okay? We didn't define what they are. Now, after the pause, we are going to inspect how those components look like. Okay? Let's do this one, and then we take a pause. Okay, people, what will you say? This one, excellent. This one has no sense. Definitely no sense. If I've got A that is not diagonal, for sure this one is not going to be diagonal. Anyway, we are going to see. This one is one of the properties that we want. Okay? Perfect. Questions, people? No?